Very good afternoon, students. In today's lecture, let us look at the design and construction aspects of the road pavements using geosynthetics. Well, all of us know that we require good pavements so that we can drive the vehicles comfortably on the roads, and some of the requirements of these roads, the road surface should remain smooth and unyielding. That is, when you drive on in the vehicle, either a car or a scooter, it should not the surface should not penetrate into the ground as how it happens when you drive on a wet mud road. Okay, it should be unyielding so that the free movement of the vehicles is ensured, and it should provide a good support in all the seasons. Okay, that is very important because these roads are open round the year, all the time, and so even in the worst of the rainy season, the road surface should provide a good rideable surface, and the thickness of the pavement, it should be sufficient to reduce the tire pressures that are applied on the at the road surface to less than allowable bearing pressure when these pressures are transferred into the subgrade. And depending on the how we construct, we can categorize the pavements into two categories. The first one is the flexible pavement. This consists of multiple layers which have very low or zero flexural strength. As you may recall, the flexural strength is the bending stiffness or the bending strength that we have with so what we studied in the case of simple supported beams and other cases. And then the other type of road pavement could be a rigid pavement like a reinforced concrete pavement. This consists of a rigid layer which has excellent flexural strength and stiffness. So no matter what is below that pavement, the load is distributed over a very wide area, thus ensuring that the rider comfort is ensured. Well, let us look at the load transfer in the flexible pavements, and the use of geosynthetics is more or predominant use of geosynthetics is in the case of flexible pavements, because in the case of rigid pavements like reinforced concrete pavements, we may not require any geosynthetics. So these flexible pavements, they reflect the deformation of the lower layers to the upper layers. That is because they do not have any flexural stiffness. Whatever happens in the lower layer gets immediately reflected up to the upper layers, and the load transfer to the lower layers is through a grain to grain contact between the particles. So if there is a good contact by way of very coarse grained particles and good interlocking, we can expect a good load transfer to the layers below. And good interlocking with very large and angular particles helps in spreading the load to larger areas. Our object is, when the load is transferred through the pavement, it should distribute over as wide an area as possible so that the pressure that we are transferring into the subgrade is reduced. And apart from the good interlocking, sometimes we may use binders. They could be bitumen binder or cement binder. Binder also can help in load spreading ability, because once you are able to bind the particles together, they may act as a semi rigid layer. And in these flexible pavements, the uppermost layer, that is the top layer, is the strongest, and as we go down, as the pressure is decreasing, we can use more inferior materials that are less stronger. So here we see an example of the wave pattern that is reflected from bottom layers. What you are looking at is a container yard that is built on extremely soft clay, and because of the applied loads, the pressures are transferred into the soft clay soil, and because this soft clay is extremely soft, it has formed a wave pattern, the mud wave pattern, and that same thing is reflected to the ground surface. And our object of constructing these pavements is this type of reflections do not happen. Whatever undulations that are there in the layers below, they are not reflected to the top surface, because once this happens, the rideability decreases and we cannot use this surface anymore. Well, here is a cross section of a flexible pavement. What we see at the top is the bitumen wearing course, that is made of bitumen or asphalt or just simply tar that we use in India, and then we have a base course and then a sub base course. The base course usually consists of very large stones, whereas the sub base course may consist of smaller stones, and this thickness of the pavement that is consisting of the sub base course, base course and then the wearing course, this total thickness T depends on the strength of the subgrade and then the traffic loading, the design life, the properties of the individual layers and so on. And here we see some examples of these base course materials. This is the WBM, waterbound macadam. Is actually these are very large size stones, and here you see the cross section of a flexible pavement with very large size stones that are bound together by using some gravelly soil, muram soil, and below this we see this GSB, that is the granular subbase, and both this WBM and the GSB layers, they are usually highly porous, so that they also act as drainage layers in our pavements. And here you see this the close up of the granular subbase layer, which is consisting of smaller size particles as compared to the base course. And the design of the pavements is based on the CBR value, the California bearing ratio, and what you are looking at is the apparatus to perform the CBR test. We take a soil specimen compacted to the desired density at an optimum moisture content as we do it in the site, and then there is a standard way of applying the loads, and we put some surcharge weight, a standard surcharge weight, and then we apply the loading at a standard rate of loading, and we get a curve something like this. On the x axis we have the penetration in millimeters, y axis the load in so many kilograms per centimeter square, and if we get a graph something like this where the load is linearly increasing with penetration, there is no initial correction that we apply, but sometimes because of initial imperfections in the compaction or in the loading, initially the pressure may not develop, and the pressure is slow to develop, and only after some time the pressure goes on increasing in linear proportion to the penetration. In this case what we do is we do some initial correction like this and shift the origin here, and we need to look at the loads at two different settlements, 2.5 millimeters and 5 millimeter settlement. This is as per the standard course of practice, and we get the loads, and then the CBR value is the load that we measure at either 2.5 millimeters or 5 millimeter settlement divided by the standard load multiplied by 100%. So this is these are the standard loads. At 2.5 millimeters the standard load is 1370 kgs, and at 5 millimeter settlement it is 2055 kgs, and we can calculate the CBR value, which could be even higher than 100% depending on the load that we measure. And the US Army Corps of Engineers, they were the first ones to suggest the thickness of pavements depending on the type of loading that we have, and here we see some very highly empirical formula where the T thickness is given in terms of centimeters, square root of P multiplied by square root of 1.75 by CBR minus 1 by pi times PC, or by taking this P inside this square root, we can write the thickness, that is the thickness of the pavements, as square root of 1.75 P divided by CBR minus A divided by pi, wherein our T is the thickness of pavements in centimeters and the P is the wheel load in kgs, and the CBR is the California bearing ratio in percentage, and the small PC, this quantity, that is the tire pressure in so many kgs per centimeter square, and capital A is the contact area, which is nothing but the wheel load divided by the tire pressure that we see here. And we see that the thickness of the pavement is very much dependent on the load that is coming from the wheels, and then the CBR value, and then the distribution area, the tire contact area. And this is another formula once again proposed by US Army Corps of Engineers, wherein they have given the thickness in terms of some more parameters. Actually the C is the coverage ratio, and P by 8.1 times CBR minus A by P to the whole root. Once again we see that the thickness of the pavement is a function of the wheel load and inversely proportional to the CBR value, and as the tire contact area is increasing for the given load and given tire pressure, our thickness of the pavement decreases. And this is another formula, is actually the earlier ones, they do not have the number of load passes and then the allowable rut depth. The previous formulas that we saw, they are for standard rut depth of 75 millimeters, and here we have two more parameters, n, that is the number of traffic passes of a equivalent single wheel load, standard equivalent single wheel load, and then the P is the wheel load, and R is the rut depth, that is given in terms of millimeters or centimeters, and then the Cu is the undrained cohesive strength of the subgrade soil, either Cu or CBR, both are linearly related to each other. The Cu is approximately 30 times the CBR in so many kilopascal units, and the Indian Road Congress IRC is also given the thickness of pavements in terms of the subgrade CBR value, and these are given for standard axle loads of 8170 kgs, that is approximately equal to 80 kilonewtons, and this is given in terms of so many millions of standard axle loads, the MSA for 10 MSA, 20, 30, 50, 100, 150 MSA, and the thickness, as you can see, it goes on increasing with the number of axle loads. So actually here also we see that as the number of load passes is increasing and the thickness of the pavement increases, and this data that is given by IRC in IRC 37 2001, that is also highly empirical, and the typical pavement composition could be the bitumen concrete, that is the topmost wearing course, is given as 40 mm up to 50 MSA, that is the millions of standard axle loads, and beyond that for 100 and 150 mm the bitumen concrete layer is given as 50 mm, and then the DBM, that is the dense bitumen macadam, thickness is linearly increasing with the higher traffic load, higher number of load passes. Then the granular base and sub base thicknesses are given as base course layer of 250 mm and the subbase layer of 300 mm. And so if we add up 40, 70, 250 and 300, we get this total thickness of 660, and these data, they are given for different CBR values, 5%, 7%, 10% and so on. And here we see the same data given for 10% of the CBR value, and as the CBR value increases, the requirement of the pavement thickness reduces. So, for example, for 150 million standard axle loads, for a CBR of 10%, the total pavement thickness is 650, and here for a CBR value of 5%, it is 770. And once again, the standard pavement BC thickness, that is the bitumen concrete thickness, is given as 40 mm up to 50 MSA, and 50 mm for higher number of load passes, and then the DBM thickness, and the base course and the sub base course thicknesses are given. And when it comes to rigid pavements, we do not have too many layers, we have only 2 layers. The one is the topmost layer, that is the rigid reinforced concrete layer, or just simply PCC layer, and because this the reinforced concrete surface itself is very hard, it will also act as a wearing course. We do not have additional bitumen concrete layer, and sometimes this RCC could be the pre-stressed concrete in order to take care of heavy loading, or in order to take care of extremely weak subgrade. Okay. And the purpose of this rigid pavements is to distribute the load over a very wide area, and this could be constructed on a prepared sub or base course layer. Basically, the base course is consisting of coarse grained particles that can act as a good drainage layer. And in this case, it should also provide a good uniform support to the reinforced concrete slab that is fabricated at the site. And the load distribution here in the case of rigid pavements is because of the flexural rigidity of the pavement layers. So, it has a very good stiffness, so it can distribute the load over a very wide area, and the design of the thickness is a function of the structural analysis. And in this lecture or in this course, we will only look at the flexible pavements, and because that is more appropriate when we are using geosynthetics. Let us now look at how we can use the geosynthetics in the case of flexible pavements. The geosynthetics we can use them in several ways. One is as a reinforcement layer. If we use the very stiff and strong reinforcement layer, it can help in reducing the subgrade stiffness and prevents the cracking of pavement due to swelling of the foundation soil. In case we have highly swelling subgrade soil, is going to undergo a lot of volume changes, either heaving or shrinking. In that case, the provision of very strong and stiff geosynthetic layer can help in evening out these volumetric volume changes, and the geosynthetics can be used as a separator or along with reinforcement function. This separator helps in preventing the mixing up of different layers, and the filter layer, it could act as a filter layer if we use as a woven or a non-woven geotextile. They prevent the piping phenomenon, and then as a drainage layer we can use thick non-woven geotextiles very near to the top surface to act as a drainage layer to lead the surface water that is infiltrating into the pavement section away from the pavement. And within the bitumen or the asphalt layer, we can use the paver fabrics to reduce the intensity of the reflection cracking, and that is one main purpose of the geosynthetics. The application of the geosynthetics we will see in some other lecture, but just to give you a brief idea, here is the separation function of the geosynthetic. Let us say that we have provided a design thickness of the aggregate layer, and which is underlined by a soft subgrade. As the time passes with the number of traffic loads, gradually the stone aggregate might just simply get disintegrated and sink into the soft subgrade, because there is not much of support given from the subgrade. Or if we are able to provide a good separator either in the form of a textile or as a geogrid, because of the restraint that is provided, the aggregate layer is preserved better, and it acts as a good pavement layer, because its integrity is preserved. These geosynthetics that we provide, because of the friction that is developed between the geosynthetic and the aggregate layer, it prevents the lateral spreading of this aggregate, because that is one form of failure. If there is nothing to hold the aggregate, once the wheel loads are applied, the aggregate will just simply spread laterally, and because of the good friction and interlocking that is developed along the geosynthetic surface, some lateral restraint is provided to the aggregate, thus ensuring a better load distribution. These geosynthetics can also help in improving the bearing capacity. See, without the geosynthetic, this could be the bearing capacity failure under a wheel load, and if we provide a reinforcement layer, this the bearing the shear surface does not propagate through this reinforcement, and the failure is within this top soil. And we have seen that whenever the rupture surfaces are prevented from formation, the failure is within the top layer, and because of that, because the failure is now in a very shallow or a thin layer of soil, the bearing capacity is much more than what it is for soil of infinite thickness. So, here in this case the bearing capacity is increased by load spreading and confinement of the soil. And another mechanism is the membrane support mechanism. When there is a good rutting, the geosynthetic is subjected to some tension, and the vertical component of this tension force directly opposes the wheel loads, and that reduces the pressures that are transferred into the subgrade soil, thereby increasing our long term performance. Well, let us look at how we can design these pavements, and before we design or before we go into the discussion of design, let us look at a dual wheel configuration, because the dual wheel configuration is very typical one in all these transport vehicles, the lorries that transport heavy goods. And how do we treat the load that is coming from dual wheels? Say if there is an axle load of P, because there are 4 wheel loads, because there are 4 wheels, we have 4 times AC, that is the contact area of a single tire, PC is the tire inflation pressure, and or in other words we can calculate the tire pressure by dividing the axle load with 4 AC. And because we have the 2 wheels close together, we need to do some empirical calculations, and if we assume that the load spreading below each wheel is something like this within a shallow depth of let us say d by 2 below the surface, we can assume that the tire pressures are independent of each other, and the pressure is just simply Pc, but below this the effect of this space between the two wheels comes into picture, and because of that the actual pressure that is transferred is lesser, and this PEC, that is the equivalent pressure, is just simply Pc by square root of 2, and this is because of this tandem wheels. And if we have only one single wheel, this is just simply Pc is equal to PEC, or PEC is equal to Pc. And now let us look at the design of unpaved roads as given by Giraud and Noire way back in 1981. They have given a semi empirical design method that is based on some analysis, some mathematical analysis and some empirical correlations, and some of the assumptions: the aggregate layer is assumed to have very high CBR value, that is a CBR of more than 80%. Usually the granular subbase material that we use that will achieve a CBR of much more than 80, usually about 100 to 150, and the subgrade soil is assumed to be a soft clay without any friction angle phi is equal to 0, and the Cu can be taken as 30 times the CBR, where CBR is the California bearing ratio of the foundation soil, and the number of vehicle passes is less than 10,000 passes, and standard axle load of 80 kilonewtons is considered. 80 kilonewtons is approximately 8,155 kgs, that is equivalent to our IRC standard axle load, and the failure is only by plastic shear that is happening within the subgrade soil. And some of the assumptions are: the subgrade soil is saturated in undrained condition, and the base course aggregate has a CBR of at least 80, and rectangular contact area of the tires, because they have considered the dual wheel configuration, and they assume that this rectangular contact area of L by B, just for simplifying the analysis, and they have assumed that the surface pressure is transferred into the subgrade soil in a pyramidical fashion, and they assume that this load dispersion angle is the same in both reinforced and the unreinforced case for simplicity, and the bearing capacity is increased from elastic to the ultimate state because of the inclusion of geotextile that we will see a bit later on. And the other assumptions is that the only failure that they have considered is within the subgrade soil, and the friction angle of the aggregate layer is assumed to be large enough to rule out any shear failure within the aggregate layer, and the interface friction between the aggregate layer and the geogrid or the geotextile is large enough to rule out any sliding failure of the base, and the aggregate layer provides a pyramidical distribution of the load P by 2, that is axle load of P, that is divided between the left side and the right side of the wheels. So we have a P by 2 of the load, and the wheels are assumed to travel along the same track along the road, so that at every cross section of the road we have similar load distribution and similar rutting, and so that we can just simply use a two-dimensional analysis. And the main assumption is because of the provision of the reinforcement, we can increase the bearing capacity factor from pi, that is 3.14 to 2 plus pi, that is 5.14, and that is based on some observations, laboratory and field observations by Barenberg and Bender that were published in way back in 1978, and they have shown that the bearing capacity of undrained clay soil is 3.3 Cu when there is no reinforcement, and when there is a fabric reinforcement placed above the clay soil, this bearing capacity factor increases to almost 6. So, this is the observation that was given by Barenberg and Bender was used by Giraud and Noire to develop their method of analysis. And here they have given their load distribution. Basically, the pressure, the wheel load is applied over a rectangular area of L by B, and the thickness of the pavement or the aggregate layer without any reinforcement is taken as h naught, and the thickness of the same aggregate because of the reinforcement is reduced to small h, and it is assumed that the load is distributed all around at some angle, and this angle is about 31 degrees, and it is assumed to be the same for both the unreinforced and the reinforced cases. And the case 1, that is the unreinforced case, and the stress on the subgrade soil because of the load dispersion is P by 2, that is the load transferred into each wheel, divided by B plus 2 h naught tan alpha times L plus 2 h naught tan alpha, where h naught is the thickness of the pavement, 2 because the load is dispersed in 2 directions, plus gamma h naught, where gamma h naught is the overburden pressure, and this pressure, the P naught at the subgrade level is equated to the elastic limit of the pressures pi Cu plus gamma h naught, and by equating these two we can get an equation in terms of the Cu and the wheel load and h naught, and by solving this h naught we can get the thickness that we require, so that the pressure that is transferred into the subgrade is less than the allowable bearing capacity of the soil. So, this is the same relation written in a slightly different form, and here if we know the C, that is the cohesive strength of the subgrade soil, and the wheel load P, we can calculate h naught. And the case 2 is with the reinforcement, and here the pressure that is transferred into the subgrade soil is P by 2 by B plus 2 h tan alpha times L plus 2 h tan alpha plus gamma h minus Pg, that is the membrane support that is given by the reinforcement. This is the vertical component, and here now we assume a general shear failure. So, that is 2 plus pi times Cu, that is our bearing capacity, and by equating these two equations 4 and 5 we can get this equation, the pi plus 2 times Cu is P by 2 times this whole quantity minus Pg, where Pg is the additional support that we get because of the provision of reinforcement, and this the Pg is the membrane support is related to the strain that is developed and the secant modulus like this, and the strain developed is also a function of several other factors that we will see in a minute. The Pg is written as k times epsilon by a times square root of 1 plus a by 2s times square, where the s is the settlement below the wheels, and the a or the a and a prime, these are just the chord length of the the surface ruttings, and the epsilon, that is the strain, is written as B plus B prime by A plus A prime minus 1, where B and B prime, they are the curved lengths. This is actually, the shape is assumed as a parabola, and this length B and B prime, that is before and after the load application, and A and A prime, these are the chord lengths before and after the load application. And once we have these values, you can calculate epsilon, and S is the settlement below the load, that is related to the rut depth. Actually the rut depth is, say if there is some soil heaving, the distance, the vertical distance from the heaved portion up to the bottom depression is the rut depth, whereas the settlement is the depression measured from the initial road surface. And if we know all these quantities, we can calculate the epsilon, and once we have the epsilon and the other factors, we can calculate the additional support that is given by the geosynthetic. And there are different cases that are possible. A prime less than A, and the epsilon can be written as B by A minus 1, and S is related by this, and A prime is A. We can relate the different parameters like this, and the design procedure is very simple. We need to calculate H naught, that is the aggregate thickness, from one of the governing equations relating the stress that is transferred into the subgrade soil by load dispersion through a height of H naught. And step 2 is to calculate the thickness of the aggregate layer with the geotextile or the geosynthetic, and we can calculate the reduction in the thickness delta H as H naught minus H, and calculate H naught prime, that is the aggregate thickness without geotextile when the number of load passes is considered, because the previous equation is only for one single load application or the constant load, and we need to modify the earlier equations by considering the number of load passes. And the final step is calculate the thickness of the aggregate as H prime is H naught prime minus delta H, where H naught prime is the aggregate thickness for the unreinforced case without any reinforcement. And for the purpose of considering the influence of the number of load passes, the Gerard and Noire, they have used this expression that was proposed by Webster and Alford. Actually this is also from the same group, the US Army Corps of Engineers group, who said that H naught prime is 0.19 log ns divided by CBR to the power 0.63, where ns is the number of passes of the standard axle load of 80 kilonewtons, and this particular relation is given for a rut depth of 75 millimeters. H naught is the thickness of the aggregate layer in meters, and this particular equation is very restrictive, because this is only considering a standard axle load of 80 kilonewtons, and the Webster and his co-workers, they have given an extrapolation for other wheel loads, and for any other wheel load of Pi, the number of load passes Ni is related like this: Ns by Ni is Pi by Ps to the power 3.95, where Ps is the standard axle load of 80 kilonewtons, Pi is any other axle load, and Ni is the equivalent number of load passes as compared to Ns. And they have also, Webster and his co-workers, they have also given an extrapolation for other rut depths, because the previous equation is for a rut depth of 75 millimeters, and we can replace log ns in this equation by another empirical equation like this: log ns minus 2.34 times r minus 0.075, and this is for rut depth larger than 75 millimeters, and as we see, as our allowable rut depth is increasing, the thickness of the aggregate layer reduces, and by combining these equations we can get a more generalized formula for calculating the thickness of the aggregate layer as h naught prime is equal to 119.24 log of n plus 470.98 log p minus 271.01 r minus 2283.34 divided by Cu to the power 0.63, where h naught prime is the base course thickness for so many number of passes and so much of axial load, and then the Cu is the undrained shear strength. And Giroud and Noire, what they have done is they have gone through this equation and they have developed a standard design chart that gives on the x axis the CBR value and the y axis the h naught prime and the delta h for standard axial load of 80 kilonewtons and rut depth of 300 millimeters and the tire pressure of 480 kPa for different modulus values of the reinforcement layers ranging from 10 all the way to 450 kilonewtons per meter, and this we can utilize for designing the thickness of this the aggregate layer for reinforced pavements. And it is actually a very simple way of applying this equation, and here we also have the number of load passes n of 10, 100, 1000, 10,000, and you see that as the number of load passes is increasing, the thickness requirement of the aggregate is increasing, and then as our reinforcement modulus is increasing, we need lesser thickness of the pavement material, and we will see how to apply this design chart for design purpose. We will see one example in the next class, along with some more aspects of the use of geosynthetics in the flexible pavements. Okay. Thank you very much.